Now that we've covered some kind of the theoretical ideas of how and why molecules form, some of these electron ideas, let's look at some examples of actually forming a variety of molecules. All right, so I have kind of this basic idea of Lewis structures. So what we want to be able to do now is predict Lewis structures. So you're given a molecular formula and you want to take that and come up with what the Lewis structure for that molecule is. So we have some molecular formulas: ClF, HBr, H2O, and CO2. And we want to work through the process of getting them, bonded up together. And so we're always going to want to start with coming up with those valence symbols for each atom, right? Draw out our valence symbols for the atom, kind of characterize what do they need and how can they share electrons to get there, right? How many bonds does each atom want to form, which is a question of how many more electrons do they need for a full valence? Also, how many unpaired electrons do they have? And then we're going to form bonds such that all atoms have the desired amount, right? Just pair up the unpaired electrons until you're done. So we'll start with ClF, chlorine fluoride. So ClF, they're both halogens. So chlorine has 7 and fluorine has 7. And so we can see right away, unpaired electron, unpaired electrons. Those probably want to pair up. Everything else is already paired. So they're just going to share that as a shared electron, right? And at that point in time, they started each with 7. You form one bond, that gets you up to 8. And so each one would have a full octet at this point. So we know that that's happened. If we want to be able to characterize and kind of quantify those numbers, we can take a look at our different atom types. So let's look at fluorine. And we said that each atom wants an octet. So how do we get to those 8 electrons? Well, we know that each dot in those lone pairs corresponds to an electron. So we can count the lone pairs around that fluorine atom and count those electrons. So 1, 2, 3, 4, 5, and 6. So those are the 6 electrons in lone pairs around your fluorine atom. So those, if we're counting up its valence, those count. And then we also have the one bond that the fluorine is participating in. There are 2 electrons in there. So this fluorine has a total of 8 electrons that are associated with it. So that's good. That means that that satisfies the octet rule. That has a full valence. So the other atom we can look at then is chlorine. We want to make sure that also satisfies a full octet. So we can look at the lone pairs. Those single electrons count the dots. And we can see again, we get 6 electrons around the chlorine atom from the lone pairs. And then we want to count the single bond again. Those electrons 7 and 8 both count for the chlorine as well. So the 2 electrons in that bond count towards filling the valence of the chlorine atom as well as the fluorine atom. Lone pairs only count for the atom they are around, but those bonding electrons count for both. So that's how we work towards filling up that valence. So we can see we get this nice full valence. This is our stable molecule, the Lewis structure for chlorine fluoride. So if we're looking at that atom, that molecule, this is what it really looks like. One single bond between a chlorine atom and a fluorine atom. Next is HBr, hydrogen bromide. So I know hydrogen in column 1 has 1 valence electron, bromine as a halogen in group 7a has 7 valence electrons. If I take a look, I got 1 unpaired electron, 1 unpaired electron. These are likely to form a bond. We know that they each can fill that up, have everything paired. So single bond, hydrogen bromide is a hydrogen atom single bonded to a bromine atom. So here's our Lewis structure. We want to always be counting to make sure we have the right number of electrons everywhere. And so I start bromine. I start with my lone pairs, count the dots. Those 6 dots in 3 lone pairs are all associated with the bromine atom. And then I have the bond. That single line is 2 more electrons. That's 7 and 8 to get me to a total of 8 electrons associated with the bromine. It's got a full valence, follows the octet rule. If I look at hydrogen now, I can see it's different. It doesn't have any lone pairs, right? So there's no electrons as lone pairs. It only has 2 electrons in its valence, right, from that single bond. And so one of the things we can see is this doesn't follow the octet rule, which again, it's a rule. So there's going to be a couple places where we don't. But what ends up happening is hydrogen is in period 1. So when it gets that second electron, now all of a sudden it looks like helium. So even though it doesn't follow the letter of the octet rule, it at least follows the spirit of the octet rule that, when it has a full valence, it only needs 2 electrons. And so hydrogen will always have 2 electrons in any Lewis structure. Hydrogen's never going to have more or less. It will always be exactly 2. That's a pretty hard, not rule, but a hard fact that hydrogen just gets those 2 electrons in a Lewis structure. All right, so let's go to non-diatomics. Let's go to molecules with more than 2 atoms. So we'll do water. Okay, and if we want to look at this, we know it's H2 means I have 2 hydrogen atoms and the 1 oxygen. And again, I can see each of those hydrogens has that unpaired electron we saw previously, but now the oxygen has 2 unpaired electrons on it. And the thing we want to be sure of is that each hydrogen can only share 1 electron. So we could form 1 bond with that oxygen unpaired electron, and then we can come over here and form a bond between that one. So what ends up happening is the oxygen forms 2 single bonds to the 2 different oxygens. It only forms 1 bond at a time with each hydrogen atom, but it just forms 2 total bonds. We saw previously that the oxygen formed a double bond, right? 2 bonds at the same time with 1 atom. Here it's forming the same 2 bonds, but broken up between 2 different atoms, the 2 hydrogens, right? So we've got that nice and distributed. And so again, if we count our Lewis structure, each hydrogen has 2 electrons like we would expect. We always expect each hydrogen to have 2 electrons. That comes from just a single bond. Hydrogen atoms should never have lone pairs in a Lewis structure. They just get a single bond. So we do want to look at the oxygen atom though. So we want to count up. We know the lone pairs. It only has 2 lone pairs, so that corresponds to 4 total electrons. And then it has 2 bonds. So the first bond is electrons 5 and 6. There's 2 in that line, and then 7 and 8 in that line. So overall, we know there's always going to be 8 total electrons. In this case, they're distributed differently than we saw for the halogens, but we still have that total or that overall distribution of electrons. 8 on that atom following the octet rule. So finally, let's take a look at carbon dioxide, CO2. If I take a look at these Lewis structures, I can see right away oxygen again has 1, 2, 1, 2, and then carbon actually has 1, 2, 3, 4 unpaired electrons. All of its valence electrons are unpaired. And so, I want to be sharing these, and so I want to share together. I can see that that carbon needs to do a lot of sharing. And so it ends up, I should probably focus on taking care of the carbons. So carbon, that's going to be a pair. It can pair up with those, right? Pair up as much as possible. And then it can pair up over here and over here. So while we may be tempted to share electrons between the oxygens, it ends up that we always kind of want to focus on what needs the most help. That carbon is going to need to form a lot of bonds, share a lot of electrons. It only has 4 valence electrons. It needs 4 more to get to a full valence. So it needs to do a lot of sharing. And so, it shares all those together, gets everything linked up, shares with both the different oxygens. And so overall, we have a Lewis structure of carbon double bonded to each oxygen atom. So carbon is sharing 2 pairs of electrons with both oxygen atoms. So we can take this, we have all of our different atoms, and we want to, again, always count. So we'll start off by counting the electrons for the carbon. Carbon has no lone pairs here. All of its electrons are in bonds. But we can count electrons associated with the carbon. Each line is 2 electrons, so 1 and 2, 3 and 4, right? A double bond overall is 4 electrons. Then we can see 5 and 6, 7 and 8 from that other double bond on the other side. So we get a total of 8 electrons on that carbon atom from the 2 lone pairs, or 2 double bonds, each contributing 4 electrons. That one's a little dirty, so when we look at the oxygen, we'll make a copy of the Lewis structure. And this time, oxygen does have lone pairs. Again, it has 2 lone pairs for a total of 4 electrons. Then we can see that just like the double bond was 4, each double bond was 4 for carbon, this double bond is 4 for the oxygen. Each line representing 2 electrons that are shared between that pair of atoms. So there are 8 electrons also associated with the oxygen atom. Participation 625, question 1. How many electrons are associated with each of the indicated atoms in the given Lewis structure? 1 is the oxygen, 2 is that nitrogen, 3 is the carbon in the middle, and 4 is the hydrogen in the bottom left. This is the first question on participation 625, due Thursday, June 25th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, how many electrons are associated with each of the indicated atoms in the given Lewis structure? The oxygen, the nitrogen, the carbon, and the hydrogen. All right, so, there's a lot of, we have these Lewis structures and we want to be able to take a look at, characterizing them and understanding what's going on in all the parts. Here is a potentially familiar Lewis structure. This is for the molecule glycine is the name of this. And so we have this Lewis structure, and what we want to be able to do is kind of characterize what's going on. What are the features of this Lewis structure? And so, one thing we could ask is, well, what's the number of lone pairs? And so if I'm looking for lone pairs, what I'm looking for is dots. And in this case, I want dots in the whole molecule. And you'll notice it is by lone pairs. So I want pairs of dots. So overall, there are 5 lone pairs. Each oxygen has 2 pairs of dots, and the nitrogen has 1 pair of dots. So then the other thing I could ask is, well, how many total non-bonding electrons do I have? And so for the total number of non-bonding electrons, this is basically counting the total dots. And so I could count them all out. I'm going to get 10. I could also take my number of lone pairs and multiply by 2, right? Because we know by the name, lone pair is a pair of electrons. So 5 times 2 gives me 10 non-bonding electrons. Non-bonding means they're not shared between atoms. They're not holding atoms together. So next, I could look at some other characteristics. How many single bonds do I have? And so when I'm looking for single bonds, what I want to look for is actual single lines between atoms, right? I do not want to count double bonds, which would be a pair of lines. So if I'm looking for single bonds, I have 1, 2, 3, 4, 5, 6, 7, 8. So I can see that I can count a total of 8 single bonds. For counting my double bonds, now that's where I'm looking for this pair of lines. So this is considered 1 double bond, not 2 single bonds, right? That is 1 double bond. It's a different characterization. It's a different characteristic, right? It's a different properties. As a higher bond order, we'd expect it to be a relatively shorter bond, a stronger bond. And so as a result, we're going to call that a single double bond as opposed to 2 single bonds. All right, so now that we've counted the bonds, how many bonding electrons? What I could just do is count all the total lines and multiply by 2. I also know that each single bond is characterized as 2 electrons, and each double bond is 4 total electrons. So I can take my 8 times 2, 1 times 4, add them up. I get 20 bonding electrons. So all of the electrons that are holding this actual molecule together. And so then what I could do is I could ask, well, what are the total valence electrons? And the valence electrons are either bonding or non-bonding. So I can just take those 2 values and add them together. If we think about it, that's a comprehensive. Something is either bonding or non-bonding. So that has to be every valence electron has to be characterized in that way, giving us a total of 30 valence electrons. So that just comes from, given the Lewis structure, kind of accounting where are all the different atoms, what are all the different bonding features, and those sorts of things. We do want to also note that total valence electrons can also be calculated in a different way based off the molecular formula. What we can do is we can look at, well, what are the total types of atoms? What are the types of atoms? How many of them do I have? And how many valence electrons are they bringing in to the molecule? I know that carbon is in group 4A, so it has 4 valence electrons. So 2 of them each have 4. I have 5 hydrogens, each with 1 valence electron, 1 nitrogen with 5 valence electrons, and 2 oxygens, each with 6 valence electrons. And if I multiply or add all that up, I'll get 30 valence electrons. And these 2 values have to be equal. This value up here, this description up here, based on the molecular formula, is telling me that's how many electrons that are brought into this molecule by all these atoms. And they have to come from somewhere and they have to go somewhere. And so there has to be a feature in the periodic table as described by this metric down here as to where those electrons are. So this is going to be an important part of any Lewis structure. Are all of the electrons that are supposed to be in the molecule there, right? All of the valence electrons that came in from the atoms, have they been assigned to a bond, to a lone pair, somewhere? So that's something that always must be true. A Lewis structure is automatically disqualified as being accurate if it doesn't have the right number of valence electrons. You can't just make up what the molecule is. Those electrons have to be there. They have to be somewhere assigned to something. Lone pair bond doesn't matter, but it has to be there. Participation 625, question 2. The Lewis structure of N2F2 is shown below. How many of each of the following are there in a molecule of N2F2? Number of bonding electron pairs, number of non-bonding electron pairs, number of single bonds, number of double bonds, number of triple bonds. Is the second question on participation 625 due Thursday, June 25th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, the Lewis structure of N2F2 is shown here. How many of each of the following are there in a molecule of N2F2? Number of bonding electron pairs, non-bonding electron pairs, number of single bonds, number of double bonds, and number of triple bonds. All right, there were 2 questions on participation 625 in this video. 20 more videos to go. I don't think they're all going to have 2 questions each. Who knows? Got to watch them and find out. See you there.